Hey folks, so in this video I want to talk about the performance analysis for linear probing. Now the problem here though is we're not going to really do it because it's a little bit complicated. And by a little bit I mean really complicated. So Knuth ended up proving it. I'm hoping I'm saying that name right. He's a very famous computer scientist, but his name is kind of one of the ones that like I see a lot, but I see it in writing, never in hear it anywhere. So what's the issue though? Why does this actually end up being complicated? And the problem somehow here is that this is more of a statistical problem sometimes than like an actual like a analysis problem, right? Normally I say it's like we want to basically look at code and be like, oh, I have a loop instead of a loop, and so this is going to happen, this is going to happen. We can't really do that here because the data really matters. So what's the particular issue? Well, consider if we have an array. And we have a bunch of slots in that array. And we could be storing stuff there, right? And so let's say I add an element here. Okay, that's fine. Add an element here. That's fine. Add an element here. And so if I'm adding these elements at random, right, they're going to be evenly distributed, right? There's going to be a pretty low chance of them colliding with any of the ones that are already there. Right? And you can do the math if you want, right? Of like, as you add, right, there's a higher chance, right, you might, bump into somebody that's already there. But the problem is, right, what makes our analysis more complicated is that the instant we get another collision, we get basically a collision for the first time, everything changes, right? Because what happens, right, is that right now there are basically just one thing, there's basically they're basically all separate, okay? There's no real collisions that have occurred, and the analysis for that maybe is okay. But then notice what happens is, let's say I have my first collision, I have to add something here. Well, when I do that, right? Okay, so let's say, actually, I'll have to count up this real quick. So I believe that has 11. Yeah, so that has 11. That's basically m equal 11 here. Initially, right, things basically are, you have basically a 1/11 chance of going in a particular slot. So it's kind of like almost like your collision chance, right? So, if you're, the fourth element, right, then you basically have, the chance to collide is 3 times 1/11, something like that. But where you get into trouble, right, we don't need to worry about specific numbers, right, because I said I don't want to do the entire analysis here. But the problem is that when you have a collision for the first time, you all of a sudden have consecutive things that are full. That means that instead of having basically just, it's over here, right, it's like, well, I have exactly one thing, right, that if it collided with me, then I would have to go somewhere else. But now, right, I could have basically collisions at either of these two positions, and they would be shifted over here, right? So it's like I have a wider window of things that could go wrong, right? And the problem is that now you basically are increasing the chance that you have a collision within that little interval here on the left-hand side because it's larger. And things basically cascade. So it's like, well, that one's now larger, right? So it's got a pretty high chance, right, of colliding here relative to these two. And then, if I go in this space, all of a sudden this is even a longer region, and there's this huge chance, right? So the instant we have these longer clusters form, all hope is lost, because if I have that long chain, it's like I have 10 things in a row that are full, that means that there are basically 10 different things that could end up, colliding, and basically have to go all the way to the end, right, and go into that new space. Versus if I have just, one thing at a time, right, then it's like, well, there's a collision, then it goes right next to it. Fine, right? And so these little regions, right, cause me a whole lot of trouble because they cascade, right? The instant I start getting collisions, that increases the chance that I get more collisions, that increases the chance I get more collisions, and so on and so on. And so this becomes kind of very, very annoying to analyze, right? And more than anything else, right, it's a stats and probability thing. It's a little bit above, what we want to do in this class. Or, well, I guess we could try it, but, we don't have all that much time. So for now, we'll set aside. All right. So this is kind of our issue, right? I've summarized it here in the text, right? Problem is, right, these consecutive regions, form, right, of things that have been used up, and that causes kind of an increase in the rate of collisions. So anyways, there is a proof basically that does a full analysis for this. I'm just going to show you basically the result from it. So in this proof, they define a value called alpha, and alpha is basically the load factor, or n divided by m. So that's like, how much of it is used up, right? How much space is used up. So what is that, used for? Basically, he defined two formulas that let us basically, find out how many checks are required for search or for successful search or unsuccessful search. So Knuth basically defined two formulas that let us check, for a successful search and unsuccessful search, how many elements would be visited. So these are the formulas down here. And this is what we care about. Now, I'm going to give you guys, exact numbers of, checks in the next slide or the next video. But for now, right, basically the aim is, right, we want to have this. So we want to have this alpha equals 1/2, right? And actually we saw in the source code where we said, oh, hey, we're going to make sure that m is basically always twice n, right? That gives us kind of optimal performance. And that'll give us basically constant time for these two things, right? So these will end up being constant, well, both these will end up being basically constants. So yeah, if we want, basically you can check different load factors, put them into these formulas and figure out, how many, comparisons are going to be needed, in order to do, these two types of searches, right, or the insert. We can kind of compute that. So yeah, that's the performance of linear probing. And the next video I'll have the exact numbers for how many checks are required. And obviously it's going to be constant time, but we're going to actually know exactly how many are required.